Okay, good morning, everybody. It's a pleasure for me to be here. I would like to thank the organizers, in particular, Amit, Karen, who made it possible for me to come here and talk to you about a project. I suppose I am one of the speakers coming from a neighboring country. And to give you the present status and where are we at Sesame, which is a synchronization facility which we are setting up nearby in Jordan, which is an international effort of various countries, including Israel. So it's particularly important and a particular honor for me to talk to you about this. For those of you who don't know it, a synchronization facility is basically a set of accelerators which accelerate electrons, typically at ultra-high relativistic or energies. And electrons of this kind, as you probably know, have the property that when they're accelerated, they emit radiation. So our job consists in collecting the radiation, which is emitted by these set of accelerators, and send them to samples, which are typically hosted somewhere here in an experimental station. Now, what is good about synchronization that it covers a very wide photon energy or wavelength range, so that it's applicable to a number of different samples, from isolated atoms to living systems. So it's an ideal place where different scientific cultures meet, and where, in order to make an experiment, you have to put together people with different scientific backgrounds, and you can discover aspects of matter which you cannot find with other means. Because of this, so this is typical things that you can do. So basically the source is somewhere here, it's the electrons accelerated, you put some optics in between, and you focus your photons onto a sample, and depending on the type of process you focus your attention of, your photon-matter interaction, you can get different information about the sample you're looking at. And as I said, the sample can be almost anything. As I always say, you can go from isolated atoms to human beings. So imagine the variety of applications. Because of that, there are several sources of this kind in the world. If you look at this map, you see that most of them are concentrated in Far Asia, Europe, and Northern America. There are a few. There is one in South America. There is one in Australia. Something is going on in India, but very little is going on in the Middle East. And indeed, that was one of the reasons why some 30 years ago, a group of people thought it would have been a good idea to start a synchronization project in the Middle East. One of them being, I would like to mention just one name, Eliezer Rabinovici, who was one of the fathers, or is one of the fathers of this project. After some discussion, the site was identified to be in Jordan. This is where it is. It's the northern part of Jordan. So it's not far from from here. We are about here, if I'm not mistaken. This is where we are. Sesame, as I said, is an international organization, and this is the list of members of Sesame. As you can see, it's an unusual combination of members, to say the least. And all these members are actually working together to this project, which, of course, as you can understand, has both scientific and political aspects. Because of this combination of members, there is a lot of interest in the rest of the world, And as you can see, the list of observers is quite long, and it's getting longer and longer year by year. As you can see, basically most of Europe is there, the European Union is there as a whole, United States of America, Russia, China, Brazil, and others are members, are observers. And observers play a crucial role in various aspects, both for training of our staff and users, and providing instruments and help of various kinds. Okay, so that is, from this institutional point of view, it copies the model of CERN. So it's organized exactly like a CERN, but we have a council. By the way, the council meeting is next week. And the representative of the members are those who are actually owning or running the facility. From the technical point of view, the original idea of Sesame was just rebuilding an old accelerator. After the fall of the Berlin Wall in 1989, Germany, the reunited Germany, decided to build a new synchronization laboratory. The old one was called BESSY, and the new one is called BESSY 2. And so there was this equipment which became available for other uses. After some discussion about upgrades and how to make best use of this, this instrumentation, it was decided that because, as I've shown before, one of the aspects of one of the goals of our project is to help reversing the brain drain issue, which affects a lot of the members. Rebuilding an old synchrotron, as I always say at this point when I give this presentation about Sesame, I'm old enough to remember the excitement of the first electrons running around in BESSY 1 because I happened to be postdoc in Berlin at the time, but that was in 1982. So BESSY 1 was actually an accelerator which was conceived in the late 70s. So if you want to reverse the brain or contribute to reverse the brain drain, you don't want to offer a facility which was designed in the 70s. For this reason, after a few ideas of upgrading the original accelerator, it was decided to use the donation from Germany as injector into a brand new storage ring. So what we have now is this very large accelerator, very large. I mean, this accelerator, which is whose circumference is 130 meters, this is basically the old BESSY 1, which reaches an energy of about 0.8 GeV, which we use as injector to a large storage ring, which has an energy of 2.5 giga-electron-volt. So, and it is a so-called third-generation synchrotron radiation source. Now, the installation of this new storage ring started almost 2 years ago. At the beginning of 2016. This is a picture we took in February 2016 showing some of our engineers and technicians. This is the technical director at the time, Erhard Huttel from Germany. And the other two persons, this guy and this, and this guy, are coming from CERN, because CERN plays an important role in the development of Sesame, and they came to help us in the installation of the storage ring. Italy also played an important role because Italy provided some instrumentation in kind. They provided the RF cavities, which are shown here. All of them have been installed. So this year, I mean, the installation of the storage ring went on basically for the whole 2016. In 2017, so this year, we started the commissioning. We had the first full turn of electrons in January this year. And then, as you can see, in a couple of months, we reached the situation in which we had multi-turns, and we were actually able to ramp the energy up to 2.5 GeV, which is a specified current. Without going into the details of the machine commissioning, I can tell you that nowadays, I mean last week, to be more precisely, these are the performance of the storage ring. So we can routinely operate at 2.5 GeV. We inject routinely more than 100 milliamps in the storage ring, and the lifetime at injection is of the order of 10 hours, and it increases, of course, over time. So this is compatible I mean, we are approaching the target values, which are 400 milliamps and a lifetime of 16 hours. We already reached the situation which, as I will show you in a minute, the beam can be fully utilized by the existing instrumentation. We are starting our scientific activity with 4 beam lines. That's how we call these pipes coming out of the storage ring. They were decided in a couple, I would say, 6 or 7 years ago. And they are listed here. One is for X-ray absorption spectroscopy and X-ray fluorescence spectroscopy. And this is a reconstruction of a donated equipment from the Helmholtz-Zentrum Dresden-Ronserdorf, and it was installed at the European Synchronization Facility. We are building a brand new infrared spectrum microscopy beamline, and we are rebuilding a donation from the Swiss Lloyd source, a material science beamline for powder diffraction studies, and a beamline for macromolecular crystallography, which is again brand new, and it is partially supported by the Jordanian Scientific Research Support Fund. Now, at the moment, the first beamline, which in chronological order is the X-ray fluorescence, X-ray absorption beamline. I'm showing here some moments of the installation. So this is, you can see the radiation safety hatch and the first mirror being installed in position. This is a phase during which the movement, we needed a lot of reverse engineering to understand how the movement of the crystals and the optical elements in general was to be achieved. So here you see 2 of our engineers testing the movements and the reproducibility of the movements. Sorry, I'm going back, sorry. And this is the experimental hatch, which is a standard X-ray absorption spectroscopy setup. This is a detector for fluorescence, and these are 2 X-ray detectors to measure the incoming and the transmitted photon flux. We started the commissioning of this beamline whenever we got, as soon as we got a stable electron beam. So we started opening, we first opened the shutters of this beamline last October, so on October 11th, more precisely. And after 1.5 months, we saw the first unequivocally monochromatic beam. And I'm showing you how we did it. This, by the way, that happened on November 22nd, which was the day in which I sent my abstract to Amit, who was pushing me to, why don't you send me the abstract? And I was telling him, wait just another day, we're almost there. And finally, I could send an abstract saying that the monochromatic beam was there. So Amit said, okay, I forgive you because it was worth waiting 2 weeks before you could write that. So this is the spectra we measured. This is a bronze plate, which was basically an alloy containing both copper and zinc. And you can clearly see that if you go above and below the zinc K edge, you see the zinc features, or you don't see them. So that is a clear indication that the beam is indeed monochromatic. So remember this date. So all what I'm going to show you in the next about the XRF beamline has been obtained after November 22nd, so in less than 1 month. So in less than 1 month, the first thing we did was we measured the, so after some struggling, on December 4, so this month, we measured the first copper K-edge absorption spectrum. So for those of you who are not in the field, that might mean very little. However, if you compare it with what is measured elsewhere, you can see that we are not that bad. Actually, this on the left side, you see a comparison of the spectrum with similar spectra measured at the Advanced Photon Source in Chicago, while on the right-hand side, you see a spectrum of a similar sample measured at Elettra in Italy, which is better resolved, but the better resolution comes from also from the fact that it was measured at low temperature. The photon flux we have is comparable to the best beamlines installed on similar machines, as it is 7 by 10 to the 11th photon per second. And we also measured the extended X-ray spectrum, absorption spectrum. And again, I'm showing here a comparison between what we can measure and what was measured at Elettra in a similar time. And you can clearly see, those of you who know a bit about access will recognize these peaks are associated to the first, second, third, and fourth near neighbor in the FCC structure of copper. And you can see that the agreement is extremely good, apart from the fact that the higher distance contribution is less intense, but this is compatible with the fact that the spectrum was measured at room temperature rather than at 10K. Then we turned our attention to some samples we have, which were provided by one of our members of the Sesame User Committee, which is committee which takes account users. And by the way, the reference person for Israel for the Sesame User Committee is Roy Beck. Where is Roy? Roy was somewhere in the audience. There he is. So if you want to know more about Sesame, how to access it, is the person you can talk to. So Kirsi provided us with some ancient human remains. These are a bone and a teeth. Don't ask me details about where they were found because I really don't know. But this is the elemental analysis which you can do using X-rays. But you can do more than that because if you look, for example, at the copper content of both samples, you will find that the content is very similar. But if you look at the near edge structure, as we did here, you can see that the chemistry is very different. And so the analysis is still going on. We're trying to understand why they are so different, but really you can see immediately by the intensity of this feature here that the chemistry around the samples is completely different. And this is the extended X-ray absorption fine structure on the same two samples, and you also see that the long-range distribution of atoms around copper in these two type of samples are completely different. So we're still in the process of analyzing the data. The data were obtained, as I said, 2 weeks ago. But that tells you how powerful our instrument is if in just 3 weeks we could obtain so much data. We actually also analyzed a soil sample. This is a soil sample from Jordan, which shows an awful number of elements in it. We concentrated on uranium, which is shown here. And we were able to measure the L3 edge of uranium, which is important both for the sample itself. This is the sample we measured compared with uranium dioxide and a mineral, an uranium-containing mineral. And that not only is it important for the soil study itself, but also tells us that we can easily operate the beamline at high energy range, so around 20 keV, and we again were able to measure the extended range structure, and this is being analyzed. So that was obtained since beginning of December. So that's, I think it's a good achievement for the first beamline. The second beamline is under installation. This is a picture showing our beamline scientist, Jean Kamel, with our good friend, Paul Dumas from Soleil. The first part of the beamline has been installed, and the installation will be concluded in January, so stay tuned. As of February, you will hear very nice results on this beamline too. At the moment, we have already an experimental activity going on with the standard Glober source installed on the microscope. And for example, one of the studies which were done was on breast tissues, studying the difference between an healthy breast tissue and a cancer containing breast tissue. And this is one of our users, Sohaila Rehman from Pakistan, who is also a member of the Sesame user committee now. And we already published a couple of few papers. These are two of them produced with the standard source, which we have in our microscope. And the advantage of synchronization infrared is that you can really have many more photons per unit area, and therefore we will be able to see details of tissues which are not available at the moment. These are a few slides about the third beamline, which will be a material science beamline, that it will receive power from this insertion device, which is called Wiggler, which basically enhances the intensity by an awful lot. So you get a flux which is of the order, an outgoing flux of the order of 10 to the 15 photons per second. And while for micromolecular crystallography, which is partially supported by the Jordanian National Support Fund, and we have designed an in-vacuum undulator, which is a special device providing a short wavelength radiation. And not only did we design the undulator, but we actually opened a call for tender. We received 2 quotations which are being analyzed, comparing prices and performance of the 2 quotations we've got, and we hope to sign the contract before the end of this year. We had a call for proposal beginning of this year. This is a list of proposals which we got, ranked, you can see the country refers to the institution of origin. You may notice that one country is missing, so please do something about it. And we have a proposal review committee, which is formed of international experts from various parts of basically Europe and United States. Soon, at least for the XRF, XAF's XRF, we will give feedback to our users and they will start coming. We have an Open Sesame project which is supported by the European Union. The European Union is giving a lot of attention to Sesame. I'm just talking about this. This is interesting because it offers the possibility of exchange training and for both our staff but moreover, more importantly in this respect for users, so that people from our members can actually go and start doing their experiments in other laboratories in Europe and be able to prepare the experiments for Sesame. As I said, the European Union is giving a lot of attention to Sesame, and there is at the moment an open call for an entire beamline, new beamline to be installed at Sesame, entirely supported by the European Union. So the budget for the call is 6 million euros. So we think we can do a very nice beamline for the user community in our region. Not only that, the European Union is supporting a 6 megawatt photovoltaic solar power plant. So that is going to be installed next summer. And that will allow, in the long run, Sesame to be the first synchronization radiation laboratory entirely running on renewable energy. So, concluding, Sesame provides the region with a unique research infrastructure and forces basic and applied science. It will foster the local development, both by using directly the X-rays we're producing to study new material, and as it happened for other large laboratories, by applying the methods we are developing at Sesame to other community, to other aspects. You know, for example, we always have this wonderful example of the World Wide Web, which was developed at CERN for what CERN was needing, and now it's used by everybody. But the most important thing I want to say today is that Sesame is not a promise anymore. It is reality. We've started the experimental activity, and I'm very glad that this is the first time I can announce that. Thank you very much for your attention.